right. Those aren't even the ones we're doing today. Oh, sorry. I'm trying to do a few things. I was recording some videos right before class and then moving from conics in my brain to matrices. So we'll switch over to that. So hi, everybody. Slight technical difficulty. YouTube was being weird. I don't know why the stream was streaming, but it took like a couple minutes for it to recognize that it was streaming. That was kind of weird. So if there's anything weird on the channel, let me know. Like if you're on the YouTube stream and something's not right, just let me know in chat or something. Thanks to everyone who's thrown their names in there. That's great. I'll take roll in a little bit. And we will get to this. Actually, this stuff we won't even get to. Let's just get that out of there. That was for the videos I was filming right before class. So we'll get to the other stuff. And then also let me grab the textbook because I'm gonna rely a lot on the textbook today. Oh, it's making me sign in again and everything. I'm going to rely pretty heavily on the textbook because writing matrices is a huge pain, trying to do it in a way that is convenient on screen. So I'm just going to rely on the book a little bit more today so you don't have to sit there and wait for me to write out matrices all the time, which is kind of a pain. So let's see, where are we? And then I have a few announcements to talk about. Where's the book? Ebook. Here we go. Okay, so like I said, I'm going to rely heavily on the textbook because there's a lot of visuals, a lot of those kinds of things that are just a lot easier to refer to what they have set up in the book than for me to do it from scratch. So, couple things that I'd like to announce that are important to many of you. So, the retake exam. So, your scores have been graded and uploaded, and it took me forever even to just get everything printed and organized. So that I could grade them. That was a horrendous grading experience. We won't be doing it like that again. So just so you know, the test that we take next week, so the final exam, you will take a week from Thursday, which is good. We have 3 sections of material left. So that's today, Thursday, and Tuesday. And then your final will be a week from Thursday. You will have a practice exam just like you had before. You will not have a chance to retake the exam 2. I will talk about exam 1 retake in just a moment. So you'll have a practice final. You will, and basically what we're going to do is I'll make an electronic file. So it's basically you're going to take the final exam in MATLAB. My math lab, but then you're going to have to upload your work so that I can look at your work and make sure that, you know, you actually did all the problems and that kind of stuff. So we're going to do it a little bit differently, but that's how that's going to work. I'll give you more details as we get close, but again, I promise I will get you like a practice test and all that kind of stuff. Let's stop playing that noise there. Okay. So, so about the retake. So it's, you know, I think kind of what's going on with the testing center is they've been having maybe people go on vacation or something like that because it's summertime and there's barely anyone using their testing center. So, you know, like that's why we had before, like there was confusion with the times and stuff like that. So I've sent the retake test to the testing center and you can make appointments. But what I have to say is last week is the next week of class, and if they're only open on Mondays and Tuesdays in July, that means Tuesday is the last day for you to take the retake, which means if I'm someone who is planning to take a retake for exam 1, I would make that appointment today with the testing center so it's available to me to do whenever, either Monday or Tuesday of next week. When I'm able to do that, then I would do that. So don't procrastinate, because if you don't get that test retake done by Tuesday, you're not getting it done. So I know there was at least one person, and I think maybe it was just one person who was not able to take the test because of technology difficulties on the day of the exam that we had. Go take the retake. That'll just replace your score. So that original 0 isn't going to hurt you. I'll just treat your retake as the original score. That's what happens. Remember, if you do the retake, it replaces your original score. I just want to make sure that's clear. So if you got a 90, maybe just live with your score, because what if you go in and you get an 80 this time? Now you've just lowered your grade. So I kind of would recommend, if you got a score you can live with, to live with it. But if you're someone who it's going to keep you from getting a grade that you think you need in this class, then do the retake. But just remember, like students, there's always this assumption that students are like, oh, well, the retake, some students, not all of them, some students will say, oh, but you take the best score, right? Like, no, I want to make it very clear. If you take the retake, that replaces your score, right? Because the whole philosophy is you're proving to me that you have a higher level of knowledge than when you took the test the first time. Let's say you got a 60% on the test the first time, and you come back now and you take it and get an 80. Then what you're proving to me is I now understand it at an 80% level, and before I understood it at a 60% level, and I say, okay, that's fine. Then I'll give you a grade of an 80% level because that's what you scored at. But if you scored it an 80 and then the second time around you get a 60%, then it works the same way, which is, well, you only know this material 60% well, so you get a 60. So just be sure, only do the retake if you are willing to replace your original score and you're comfortable with that. Also, make sure you're eligible for the retake. Remember, that was people who took it in the testing center can do a retake. People who took it online with their video camera on can do a retake. If you miss the test completely, you can do the retake. That's kind of the only way that you're going to do that. But if you took it online but with the camera off, then no retake in that situation, okay? So don't procrastinate. Summer moves so fast. You got to get that done. So I would make that appointment today, and then make sure you have an appointment set for next week, and then don't miss it because there's no time. The semester ends at the end of next week, and we have to get grades in as fast as we can. Plus I'm going to be out of town that weekend, so I can't accommodate anything anyways. I got to get grades turned in and leave town. So yeah, so that's the retake. If there's any questions about that, make sure you ask today, because then I can answer your questions. Otherwise things are going to start moving along. So let's see, there's a couple comments here. Oh, okay, we've got some names there. And I'm not seeing anything else, so it looks like maybe YouTube got up and running. It was super weird trying to get the YouTube stream started today, but anyways, it looks like we're past that. Next order of business, homework extension. So I know I keep extending homework and then saying, okay, everybody, I'm not going to extend any more homework. And then, here we are extending homework again. So I know that my math lab had some very poorly timed maintenance. Sometimes that happens where they plan to do maintenance for like a few hours or a day, and then it turns into like days, or in this case, I guess most of the weekend. So that's a big chunk of opportunity to work on the homework that you didn't have. So I've extended some homework dates. So if you still want to go back and work on those homeworks, you can. Just kind of be aware we're at the end. I can't really extend homeworks that much further, so make sure you're good with that, basically. But you can still work on that. There was one semester where my math lab wasn't working right for weeks. We had students struggling to get homework done for weeks. That was a nightmare. That was a huge headache. It really unfair to the students, but at that point in the middle of the semester, like, what are you going to do? There's not much we could do about it. So it's kind of a pain. But luckily, this was only a weekend, so you get a few more days to work on those homeworks, so no one's being cheated out of it. It's just you might be a little busier this week than you were planning to be, but I'm going to make sure you have that. Let's see. What's the question here? So our next exam is our final. Yes, so your next exam is the final, and that exam will be the last day that we meet for the course, which is Thursday, a week from Thursday. So like 10 days from now, something like that, a week from Thursday. Yeah, that's how that will go. Okay. So, and it'll just be during class. The test will be during class. We have 3 more kind of units. I've sectioned off 3 bits of work to do. 1 today, 1 Thursday, 1 Tuesday. Early next week, I'll release the practice exam. You all can help each other in Discord and stuff like that. Get ready for the test. And then your test will be on Thursday. Okay. Right. So the homework's been extended. And then I already talked about the final exam. So the final exam is just exam 2. I'll talk more about it as we get close. There will be a few problems from earlier in the semester. You're going to have to find the equation of a polynomial, just like you did on the first exam. So those of you who know how to do it, great. You're going to get more points again. Difference quotient, again, those of you who learned it properly, you'll get it again. You get those points again, hopefully, and be good. But we'll go over it more as we get closer. But we got to deal with some other stuff along the way. So is there any questions or concerns that are sort of standing before we move forward with the math material? No? Okay, so, big scores in the class, just to kind of remember, if you're planning to do the retake, and many of you did very well, usually in the summer, students are pretty strongly motivated, so we see a lot of really good scores in the summer. Many of you did good. I don't know if it's as good as you would have wanted to do, but many of you did quite well. And that's good to see. Even in the testing center where it's under proper conditions, many of you still got great grades, so that's really good to see. If you want to do a retake, set that up immediately, like immediately. And then the last test, so there's only one test left. Sometimes I call it the final exam. Sometimes I call it exam number 2. They're the same thing. That's a week from Thursday, okay? And your homework's been extended, so some of it. So feel free to work on that. Okay, with that said, let's jump back into matrices. So we talked about matrices. Matrices are one of those things where when you first learn them, it's very confusing because the notation is very different, and all of a sudden there's no variables. You're like, where'd my variables go? Now you're having me work in this weird box that sometimes has a line in it, sometimes doesn't have a line in it. What is going on? So let's kind of just remind ourselves what we're doing here. Oh, and I made some videos this morning on conics that I'm going to try to get up soon, so that if you're trying, there's already a couple videos up for the conics, but if you're trying to get a jump, some of you are ready to plow into the next set of material, work ahead a little bit, I'll try to get that stuff up for you in reasonable amount of time here. Let's see, where are we? Systems of equations and okay, so we talk about systems of equations, 2 variables, 2 equations. That's kind of where you start. And then you get into 3 variables with 3 equations, and we learn to do them by hand. But in reality, no one ever does those by hand because they're such a headache. It's just easier to jump into matrices at that point and use matrices. Like if I'm doing a systems of equations with 2 variables and 2 equations, I'm probably just going to do it by hand. If I'm doing 3 equations and 3 variables, I'm going to use a matrix, maybe put it in a computer. Even if I have to do it by hand, I'm probably going to do it with matrices. But maybe I'll throw it in some kind of computer algebra system or something in order to help me out with that. Partial fractions. Most of you are going to learn partial fractions in Calc 2. So if you have to take Calc 2, you're going to learn partial fractions when you get there. It's kind of silly to learn them now. And then, whatever, a year and a half from now, you're going to need it. So usually we just teach those as part of Calc 2 now. Okay, systems of nonlinear equations in 2 variables. Let's see. Wait a minute. Oh, yeah, we talked about that last time. Sorry. So I've opened the wrong chapter here. 6, matrices and determinants. So we want to get into matrix solutions. And then I have a question that I'll try to answer depending on where time is in class today. I want to make sure I get to the material we need to, but hopefully I'll be able to cover that at the end of the class. Otherwise, the student who asked about that problem, I can help you after class. Worst case scenario, I can help you with that later. Also, I put up a video that has to do with that, so it might be helpful to watch that video as well. But worst case scenario, I'll help you after class. But I want to make sure I get to this because a lot of this is like new information and it's kind of weird for people. So last time we talked about matrix solutions to linear systems. So let's just kind of review, because if you've forgotten or for whatever reason don't remember what a matrix is, you're just going to be lost from this whole chapter. So the whole idea is we take a system of equations and we convert it to this thing called a matrix. I should be able to make this a little bigger here. Let's see, it's probably too big. No, that's good. So we convert it to a matrix. We do this because, one, it's an abstraction, right? Mathematics, we abstract things naturally anyways. This is what we do. I solve one problem, and then I start thinking about, can I use what I did in this one problem to solve like a whole variety of problems? And it's called generalizing, and it's one thing that is very difficult for people in mathematics. Those of you who are just naturally good at generalizing are, that's one of those skills where we talk about, someone's kind of like scientific minded, or they're analytical minded, and they can like good problem solvers and stuff like that. That's one of those things, is that you're able to generalize. And, a lot of times you do this in your everyday life. You watch something and you kind of learn from it, and you go, I can apply that lesson I just learned to the other areas of my life, right? It's the same thing here. We're generalizing systems of equations into this form. It's kind of a general form where we throw it into a matrix. Computers prefer this. So your computer algebra systems, your MATLAB, your Maples, anybody who uses like NumPy or anything like that, for those of you who are like Python coders or anything, those are all designed to handle matrices. So as you can imagine, this is hard. Good luck going to, encoding in Python some linear equations and then hoping that it's going to do something with it. There's probably some packages out there that deal with it, but it's a pain. All your computer algebra systems and NumPy and stuff like that, they're just designed. Give me a matrix and tell me what to do with it, which is really convenient. Which is why in the future you won't have to solve big systems of equations the way we used to. I think I talked about last time. My advisor, when he was in grad school, he had this 100 equation with 100 variables to solve that took him like a semester to solve. When I was in grad school, I wrote these programs that was collecting data for me, and those matrices were thousands by thousands. You couldn't do it by hand, but it would take the computer a few hours, and it would spit it out for me, which before that it was impossible. To complete in a lifetime. Some of these matrices were so big that I had to deal with, but now you throw it in MATLAB, you go have lunch, come back, MATLAB's got an answer for you. Sometimes it would take a few days or up to a week, but it does that data for you. So that's really the future for a lot of you, is putting a matrix into a computer, telling it to do something with it. But again, you should never be using a piece of mathematics or science that you don't understand. So that's why in the beginning we have you do all these by hand, so you understand what it is. For many of you, understanding linear algebra is going to be very, very important, more important than you would think right now. So you want to, don't cheat yourself out of that knowledge. You want to make sure you have that solid foundation in matrices, because if, there's quite a few people in this class going on to calculus, you're probably going to need it in your career as a computer scientist, an engineer, a mathematician, a chemist, or physicist. You're just going to be using matrices and linear algebra regularly. So you want to make sure that you're embracing matrices and not like scared of them. I'm going to avoid those. I don't like them. If you're going to be in sciencey type stuff, you probably will need to be comfortable with matrices. So embrace them now, and then get that kind of stuff out of the way. So then we had our row operations. We talked about the what happened? Why is it not letting me scroll? It's doing that dumb thing again. Okay. There we go. That's still not right. What's going on? Let me see if I can mess with this a bit. I don't know why it does it every once in a while, where it takes away my scroll bar. This is kind of weird. Okay, anyway, so you have three basic operations. You can exchange two rows, you can multiply a row by a non-zero value, or you can take a row, multiply it by a non-zero value, and add it to another row. So those are those three operations, and those seem very limiting. It's mind-boggling the things you can accomplish with just those three row operations. So we talked about those last time, and we talked about why they're allowable, like why they make sense to use them. So hopefully you remember that. If not, go back and take a look at those. And this gives us a method for solving systems of equations. So I want to point out there's a few different forms. Just like we have different forms of a line. Remember when we were learning to solve equations of line, you have slope-intercept form, you have point-slope form, you have standard form. You have all these different forms for a line. With matrices, we have different forms. Depending on the amount of work that you want the computer to do, it's you may choose one of these forms or over the other, or what it is that you're trying to accomplish. So I talked about how if you're going to use these 3 row operations, you have to use them in the right order. If you try to use them in the wrong order, you're going to mess up your previous work. So we want to do it in a way that none of our previous work gets messed up, right? And that amounts to getting a 1 in this first diagonal position. Remember the diagonal? Those are the positions that consist of the row and column being equal. So first row, first column, that's our first diagonal position. Second row, second column, second diagonal position. Third row, third column, third diagonal position. So we get a 1 in the first diagonal position, and then you want zeros below it. So that's step 1, 2, and 3. Get a 1 here, get a 0 here, get a 0 here. If you've done that, then you can't mess up this first column anymore. I mean, you could, but you kind of have to try to mess it up. So all the rest of our work now when we're in column 2 is not going to mess up column number 1. So what you do is you get a 1 in the diagonal position, you get a 0 below it. Then you're going to get a 1 in the last diagonal position. Now this is what we call row echelon form. That is, it's in a situation where it's really easy to back substitute because this bottom line is solved for one variable, and then you're going to substitute it into this equation you have up here and solve for that variable. Then you're going to take those 2 variables and plug it into the top equation and solve for the third variable. Now that's fine, but that's a lot of work it's maybe not a ton of work, but like, why would I want to do that work? Sometimes you want things in just row echelon form, so this is something that you should be aware of, this kind of form. But there's a better form called reduced row echelon form, which fully solves the problem for us. So you'll see problems where they say, oh, here's row echelon form, use your back substitution. That just means take the variable you know, substitute it back to get the other variable, take those 2 variables and solve for the third. That's all they mean by back substitution, and you can do that once you're in row echelon form. And like I say, you may have a reason why you want to put it in that form, but generally, at least in my experience, the stuff I've done, everyone's math's a little bit different. Like in grad school, you have all these people doing math, and like no one even understands everyone's math because you're so specialized. You're in like your specific area of research. So everyone uses math differently to do different stuff depending on the research that you're doing. For me, I almost always wanted things in reduced row echelon form because the stuff I was doing didn't need row echelon form. So let me see. I'm trying to figure out what page that was on. Oh, do they not show reduced row echelon form? Oh, I must be thinking of a different textbook where they have another version for reduced row echelon form. So let's go back here. I'll show you on the row echelon form. Okay, reduced row echelon form. See, we got 1s on the diagonal and we have 0s below it. That's called row echelon form. If you get 0s above your 1s, where these little asterisks are, if you make those 0s, that's called reduced row echelon form. And it's the fully simplified, like fully solved version of your system of equations. So when you're looking at that matrix, you can just literally read back the solutions to your equation. So that's why it's nice. You don't have to go through and do any of that back substitution. You just go right to your answer and it's all done. Now, every once in a while, you can't quite get there for various reasons, but it's helpful. So there's row echelon form, reduced row echelon form. We talked about those. And then I think that's kind of where we left off with things. Yeah, okay. So now let's dive into 6.2, inconsistent. And this actually has one of my favorite problems in the whole book, of the whole course. So let me grab a water. I didn't get a water because I was recording those videos. I'll be right back. Okay, so most of the systems of equations that you have dealt with so far had the same number of variables as equations. And very frequently, if you have the same number of variables as equations, is not always the case, but a lot of times if you have the same number of variables as equations, you're going to end up with one solution. So you can think of, I don't remember if I mentioned this last time, variables give you a degree of freedom, right? Because if you have a variable, then you can play with the values of that variable. You could say, well, what about when x is 7? Or what about if x was 5 or 2? It gives you some freedom and some flexibility in your system. An equation is the opposite. An equation is a constraint that locks you in because you have to satisfy that equation. So you can think of it that way. A variable is it's almost like a knob that you can turn, and you're turning the values up and down to kind of play with it and see what makes sense. That's a freedom. But an equation says this has to be satisfied. So if you move this variable, it's going to affect these variables in this different way. So you have this balance in systems of equations between freedoms and constraints. And when those match up, that's a lot of times when you get one solution. Not always. Like I want to make it clear. You can have the number of equations equaling the number of solutions, and you don't just end up with one solution. Weird things can happen. But when your number of equations and your number of variables is different, then you're really going to get some weird behavior, right? This like not typical behavior that we've been dealing with for systems of equations. So that's what we want to look in when they talk about inconsistent and dependent systems and their applications, which we haven't looked at yet. But I'm gonna talk about what those terms mean. And if there's any questions, please ask. I don't want to leave anyone behind in the problem. So when we're dealing with these higher dimensional problems, you end up in a different. Let's go back actually. So a system with no solution. Let's look at this one. So remember when we were dealing with two equations and two variables, those were two-dimensional lines, right? They were lines on, we could graph them on Desmos and see what they did. Well, when you're confined to lines in a plane, that's pretty confining, right? There's only so many ways you can move a line, and they're not in 3 space, so they can't like miss each other. So the only way that you could have non-intersecting lines in two-dimensional space was to have parallel lines. In fact, let me pull up a Desmos and we'll take a look at it. I won't be able to do the third-dimensional analog because we don't have a graphing. You don't have like 3D graphing that is this fast. But remember when we were graphing lines, you'd have like 2x minus y equals 3 and 2x minus y equals 5, right? So this was our no solution analog. So parallel lines, right? Those lines have the exact same slope. They're running alongside each other. They're never going to intersect, and the intersection points are your solutions. Therefore, parallel lines lead to a no solution. Well, when we're dealing with 3 equations and 3 unknowns, we're essentially existing in 3 space then. 3-dimensional space is where you would graph those things. Well, there's a whole lot more freedom in 3-dimensional space since these 2 lines now don't have to exist in a plane. They could start, going completely different directions from each other. There's a lot more ways that lines can miss each other in 3-dimensional space than in 2-dimensional space. So, and again, you get that by adding a variable that gives us a dimension of freedom. That means there's a lot more different ways that these things can miss each other. Yeah, and we'll get to the dependent situation in just a second. So let's see, what did I want to say? So let's look at a system that would have no solution, right? So I'll sort of skip ahead, but I'll show you the highlights because we're not going to go through each step here. But you're given a system of equations. So notice that it's 3 equations and 3 variables. I don't want to solve this by hand. We could do it, but why would I spend 15 minutes when I could throw it in matrices and make this much easier for myself? So what you're going to do is you take the linear system, and then remember we talked last time about how to construct the matrix from that linear system. So see how remember all the coefficients match up. This line represents where the equal signs go. You got 2, 5, 12, 2, 5, 12. You can see the same numbers popping up here. Okay, so what you're going to do is you're going to go through and solve this using your Gauss-Jordan elimination, which is just that process of, in fact, you don't have to follow the Gauss-Jordan elimination. It's a procedure which you are definitely going to get to know in the future. If you have to take enough calculus and linear algebra, you will learn Gauss-Jordan elimination and how it works. But you can just use your row operations in the meantime, sort of however you want in order to get that done. Sometimes people say Gauss-Jordan, sometimes people claim Gauss-Jordan elimination is just getting those ones in the right spot and the zeros in the right spot. But some books have a very specific, algorithmic way of saying this is the right order in which to do it. So it's a little bit of a gray area depending on what book you're looking in. Anyways, you take your matrix, and you can see they're progressively putting it in into that simplified form. And then look what happens here. This gets kind of weird. Let me see if I can, that's probably risky, but let's see if I can open it again a little bigger so we can see it at a bigger level here. So look what happened. Instead of getting a 1 down in this position, that's what we were kind of expecting, right? We're expecting to get 1s on the diagonal. Look what happened. All of a sudden it's zeros all the way across. So how would you interpret that third equation right here? Well, if we were to turn this back into the equation, it would be 0x plus 0y plus 0z equals 5. In fact, they have it written right down here. So think about that. 0x plus 0y plus 0z equals 5. Well, that's really just 0 equals 5. Well, that can't be. Yeah, it's not. 0 is not equal to 5. So basically, you got an impossible situation. So it's very similar to when we would get no solutions in other types of scenarios. Where like with lines where you'd get 0 equals 5, that's what we're getting here. But it sometimes is, if people aren't comfortable with matrices and they're not comfortable yet with pulling the solutions out of the matrix and putting it back in this system of equations form, can be confusing. So just always remember, each column is a variable signs, and then this is your answer. So 0x plus 0y plus 0z equals 5 can happen. That's how you know there's no solution here, right? So that's why this is a no solution. Oops, where did I go? It's a no solution type problem. And here's kind of what I was talking about before when I was talking about the different ways in which you can get no solution in the three-dimensional plane. Look at these. We could have 3 planes that are all parallel to each other. That's kind of like the analog of the 2 lines in 2 space. This is 3 planes in 3 space, and they're all parallel. But look here. Here things are touching each other, and they're intersecting, but all 3 planes don't intersect in one point, right? We have intersecting points between the planes, but there's not one point that is on all 3 of these planes right here. And the same over here. All of these planes touch all of the other planes, but not in a single point. There's not a single point that's on all 3 of these planes. So lots of different orientations now where things can match, or where they can intersect each other, but not have a solution. Oh, and for those of you who are sort of confused a little bit, if we have 3 variables in here, this describes a plane. A plane's like, imagine this a sheet of paper that goes on forever, flat sheet of paper going forever. That's a plane. So when you have an equation with 3 variables, it's a plane in 3 space. So 2 variables is a line in 2 space. 3 variables is a plane in 3 space, generally, assuming that, it's of this form and stuff. Okay, so that's one scenario you want to look at. The no solution's the easiest one to look for because it immediately looks weird. You're like, oh yeah, I've got zeros all the way across and then a number. That can't happen, and most people pick that up pretty quick. The infinite number of solutions takes a little bit more thought and a little bit more work to make sense of. So let's jump back into Desmos for a minute and remind ourselves, how did we get an infinite number of solutions when we were dealing with 2 equations and 2 variables? Well, essentially what you had was 2 equations that were the same line, but they might look different. So y equals 2x minus 4 and say 2y equals 4x minus 8, right? Just they look different. They have different numbers in them, but look, they're the same line. You can see they're the same line. They're right on top of each other there. That's the main way that you get a dependent, this is what we call a dependent system in two-dimensional space, is that one line is just a multiple of the other line. And sometimes we move the terms around so it's not obvious. Like when you look at it, you don't go, well, that one's just double the other one. Like it's kind of mixed up, so you don't see it right away. But that's how we do it in two space. Now in three-dimensional space, again, things get much more complicated. So you can have what we call a linear dependency. This is a more of a generalization of what you can expect with linear dependencies. It just means that one of your equations is a linear combination of the other ones. It's just that that idea is so restricted in two space that it kind of oversimplifies itself. So what you could have was, let's say you have three equations. That third equation might be 2 times the first equation plus 5 times the second equation equals the third equation. Well, you're not going to recognize that just by looking at it. You're not going to look at it and go, well, clearly equation 3 is negative 4 times equation 1 plus 11 times equation 2. You're probably not going to see that right out of the gate. But so they're hard to recognize like immediately. But as soon as you start doing your Gauss-Jordan elimination, it's going to pop out, right? Just like it did with no solution, except the difference here is, notice this time we get zeros all the way across. That is allowable, right? That is a true statement because what we have here is 0x plus 0y plus 0z equals 0. Well, that's true. Before, a minute ago, we had 0x plus 0y plus 0z equals 5. That's false. That's not true. That leads us to a no solution conclusion. But here, well, here we got zeros all the way across, and that is true. So what really happened? What happened was when you were doing the Gauss-Jordan elimination, it basically canceled out that third equation, which is really just repeated information. If equation 3 is a linear combination of the first two equations, then equation 3 doesn't give you any new information, right? It's just repeating old information that you had. Each equation has some information encoded in it. That's why we have to use all these equations when we're solving systems of equations. But if my third equation is just a linear combination of the first two, there's no new information, and essentially it just goes away. Right? That's what we're doing when we're simplifying these is we're getting rid of redundant information, we're simplifying everything down, and that's what happens. So whenever you see this with zeros all the way across, you know you have a dependent system. And you can get multiple lines with zeros across, right? You could have 10 equations and maybe 8 of them are dependent. You're probably not going to have that, but maybe 8 of them are dependent. So, just sort of be able to recognize that. So you start with the system of equations, you put it in a matrix, you go through, you do your row stuff, all of a sudden, boom, zeros all the way across. That means a dependent system. That means one of your equations is based on the other ones. But what that means is your system really only needs 2 equations. So you still have 3 variables, but only the 2 equations that you have to deal with, right? So in that case, if you have more variables than you do equations, and it's simplified, right? Like you've gotten rid of, the extraneous information, you've simplified things down, and you still have more variables than equations, you're going to have an infinite number of solutions, okay? That's just how it works. Because remember, your variables are like degrees of freedom, your equations are constraints or restrictions. So if you have more variables than you have constraints, you end up with this infinite number of solutions, right? And I'm talking a little generally. I mean, assuming you've done your simplifying and all that kind of stuff. And we'll take a look at how exactly we want to describe that. So here's generally what we do. This is the easiest way to do this because you go, okay, well now what? I've gotten down to a situation where I have 2 equations with 3 variables in them. So this one has an x, y, and a z, and this one has a y and a z. Notice how they both have a z in them, this third variable, there's a z there. what we usually do then is we try to write things in terms of that variable. So that becomes our independent variable, right? So the first equation has an x, y, and a z. The second one has a y and a z. Now, if you wanted, you could decide that y was going to be your independent variable. But usually we're going to go with z. But there's, every matrix is a little bit different, so you got to play different games. So see what they did here where they went and they solved for x in terms of z. And then over here, they went and solved for y in terms of z. So x and y have both been solved in terms of z. Now, why is this convenient? Because it means that I only have to pick a z value, and my x and y are determined. That gives us a lot of control. That means we just have one dial that we're turning, the z dial. We can kind of turn that dial and see what it does, and our x's and y's automatically adjust because they are the dependent variables. So that's kind of nice. Instead of having 3 dials and you're turning an x, y, and z dial to try to get the right thing, you're just turning the z dial and the x's and y's are automatically adjusting. That's why this is really convenient. Okay. So like they do that here. Well, what about when z equals 1? Okay, we'll plug it in and boom, you get your x and your y automatically. And since this is usually going to be happening in a computer, that gives you really fast ways of like trying things, and well, there's a lot to learn in linear algebra. Like I say, some of you will take entire courses on this kind of stuff. So what do we do here then? We end up with, we want to write this as a solution, and remember our solutions can be written as tuples, except in this case I guess they're, do they call them truples? Triples? Triples is what they call them. So there's 3 things here. There's an x, y, and a z, and we pick an x and a y and a z. But we have these constraints, as we saw up here. As soon as you pick, as soon as you pick what z is, the x and y are determined. So if we can't just write the tuple as x, y, and z, because that would imply that we are going to change all the dials, the x dial, the y dial, the z dial. But we're not allowed to do that because once we turn the z dial, the x and y are already determined. So do you see how they wrote the solution here? Where we have a spot for our x's, a spot for our y's, and a spot for our z's. So what we do is we put our z in there, and then we say, well, we go back up to these equations right up here. Well, this says that if we pick a z value, then the x value is going to be 12z plus 1. Well, notice that's what we put in our vector. The x value is 12z plus 1, and the y value would have to be 10z minus 1. So we put that here. So as soon as you pick a z value, you could pick 0, you could pick pi, you could pick a trillion, whatever you want. When you set z equal to that, it automatically knows what y should be and what x should be based on the work that you did previously in the problem. That's how we have to write those infinite number of solutions, because they actually have a structure to them. They're not just like random points out there. It's like there's a structure generally to it. So here's a way that planes can intersect infinitely. Say you have a plane and you just rotate it around a line so that it's kind of symmetric there. Then you're going to get this line going through the middle that would be described by this vector right here. So when you pick a z value, it's going to give you a point somewhere on this line. Now pick a different z value. It's going to give you a different point on the line. Now pick a different z value. And remember, when we pick a z value, it's determining all 3 coordinates. And each time you pick a different z value, it's giving you a different spot on this line here. Okay? So, and you can have, the extreme cases where all 3 planes are the same plane. That's usually not as helpful. It's usually not as interesting when you get a case like that. It usually means that you just accidentally doubled up some equations somewhere, which is not usually helpful. This kind of thing can sometimes be helpful. Sometimes it's annoying. Sometimes it solves, it gives you possible solutions. So it just depends. It might sound great, like, oh, well, I have an infinite number of solutions. Isn't this great? Sort of. Sometimes it's good news. Sometimes it's bad news. Imagine if you're trying to calculate some decision about your business, And you're like, how do I maximize profit? Oh, well, there's 10 different ways to maximize profit. Okay, well, which one am I supposed to use, right? Then you have a sort of a deeper investigation you have to go into. So, it's not like one thing that always applies to these dependent systems. You have to kind of be open to it. You have to kind of investigate each one separately because they all have their own little personality. So non-square system, so that's what I was talking about. A square system would be where the number of equations matches the number of variables. So non-square just means that, like in this case, if we have more variables than equations, so I know I'm going to have more freedom, and we're going to end up with, see how we end up with that again? We get this infinite number of solutions. We ended up with that vector. So anything I choose for z, that automatically determines my y and my x. So that's what that's going to look like. More variables than equations means you're going to end up with an infinite number of stuff, of solutions. If you have more equations than variables, assuming that you've already simplified them, then you probably have a no solution type scenario. Okay, so just look out for that. Applications. Okay, I like this application. This is one of my favorite problems from the whole course. I think it's kind of neat the way, you know, a lot of books just teach you, like, here's what happens with dependent solutions, and they're never useful. But I don't know. I find it interesting when a book actually takes a problem and says, here's how you use a dependent system, right? If you just get one solution, that's pretty obvious what you're supposed to do. That's your solution. So you move ahead with that solution and you apply it to your business or your science or research or whatever it is that you're doing. What happens when you get a dependent system? How can we use that to our advantage? So I'm gonna use this. I've sometimes put this on tests. Sometimes I don't. I don't know if I'll put it on this semester. I might. So just a heads up. I might put a problem like this on the test. I've sometimes done it. Sometimes I don't. It just depends. But I tend to like this problem. So you can imagine this kind of scenario of traffic control, right? We always tend to complain about the way traffic is, especially in Southern California, although traffic's kind of bad everywhere now. Complain about traffic and why did they design this light this way, and what's going on with this, and why did they put this road here? And it's kind of a pain. Like in Ventura, you have the 126 that goes right through Ventura, and it makes it really hard to get from one part of town to the other. You have to either be on Victoria or you have to be down by Main Street or something like that where you can cross, over the 126. But it's kind of a pain to get around. And it creates problems like, for example, a few years ago, they were doing construction work on Victoria and Telegraph. So many of you have been through that intersection in your lives. Some of you do it daily. If you go to the college, there's a decent chance you had to drive through that intersection. It's a major, major intersection in the city, right? Well, they were doing construction on that street, and it caused a lot of problems. Like, traffic was nasty, especially since there's a high school right there. Buena High School's right there. So between the construction, and then it's always a pain when school's getting out, and you'll have these, like, hordes or herds or whatever you want to call it of 150 people crossing the street together or whatever. It wreaks havoc on traffic. So the idea is, well, how do we design good traffic systems so that we know that they can handle the amount of cars that they need to handle? And then also, what if we need to do construction on one? That's going to mess up traffic. Can the other surrounding streets absorb that traffic? And you solve this using systems of equations. You solve this using matrices. Because it's hard. Like, imagine just sitting there with no knowledge of civil engineering, and you're like, well, what if we have this one road that has 3 lanes on it, like Victoria does, and we close 2 of those lanes? Is traffic light enough that people are still going to be able to get through, or is that going to cause major problems? You can't really guess at this stuff. It's not immediately obvious. You're not going to eyeball it and go, yeah, I think it's probably fine if we'll just go down to 1 lane and then the whole city kind of comes to a halt. You have to use this kind of information in order to in order to solve the problem and really have confidence in, yes, the surrounding streets can absorb the overflow traffic, or no, they can't. We better figure out, we're either going to do construction at night, or we're going to extend it and only close one lane, but it's going to take us twice as long. There's lots of different ways to do this. So we're looking at a very simplified example. These are one-way streets. Obviously, if we wanted to deal with two-way streets, it would the complexity would compound, would get much more difficult. But we're just going to kind of look at a simplified scenario for now. So we've got these streets, and the arrows indicate the direction that cars can drive. And then we've got these intersections, I-1, I-2, I-3, and I-4. And you can see here they're giving us the cars per hour that go through here. You may have seen this. I think they might even have like fancier ways of doing it now, or maybe I just haven't seen them as much. But it used to be sometimes you'd be driving through an area and there'd be like this metal box on the side of the road, like up on the curb. And then there'd be this like strip of plastic going out into the road. And you'd go like, what's that? That's weird. And you drive over it and it'd go thump thump. What that thing is doing is it's keeping track of how many cars go by so that you can get this exact type of information. So if you wanted to know how many cars go by, one way you do it, if it's like a small residential street, you just put up one of these boxes with this strip, and every time someone drives over it, boom, boom, a little clicker goes +1 or whatever. Like inside the box, it's keeping track of it. Now, you can't do it like on Victoria. That's not really feasible to do something like that. You got to have to use other ways of collecting data. But one way or another, you end up with these stats. So 700 cars per hour start here on the left and go through this intersection, go through I-1 moving this way. 300 cars an hour start from the north and come down through this intersection going south. Okay, so you can see for each road, we're told how many cars are entering, how many cars are exiting. What we don't know is what's happening in the intersection. So take one of these cars coming from the left. Well, it can't turn north because then it's going the wrong way down a one-way street. That's not good. But that car could go straight through the intersection on Palm Drive here, or it could enter the intersection and turn right and go south to I-4. We don't know that information. We don't know if the car is going straight or turning right. So there's some options here. What we do know, think about it this way, because this happens a lot of times when you're setting up equations. What we do know is that every car that enters the intersection has to also leave the intersection. If not, that means there's a car left in the intersection, and a car left in the intersection means you have a traffic problem. So assuming that our goal is to keep things flowing, then we can make the assumption that every car entering the intersection leaves the intersection. Okay? If 600 cars, or if 700 cars an hour enter the intersection from this direction, but only 600 cars an hour leave that intersection, that means we're leaving 100 cars in the intersection. That doesn't work, right? So that's kind of the key, that it's not obvious when you're looking at this, but that's how you're going to construct things, is you're going to go, oh, every car that enters has to leave. Okay. So what we do, so let me read this now that I've kind of set things up. So this figure shows the intersections of 4 one-way streets. As you study the figure, notice that 300 cars per hour want to enter intersection I-1 from the north on 27th Avenue. Also, 200 cars per hour want to head east from intersection I-2 on Palm Drive. The letters W, X, Y, and Z stand for the number of cars passing between the intersections. So W is the number of cars that go from I-1 to I-2. Z is the number of cars that go from I-1 to I-4, and so on. Okay, and you just have to keep your, remember, these are one-way streets, so we have to keep all that straight. Okay, A, if the traffic is to keep moving, at each intersection, the number of cars entering per hour must equal the number of cars leaving per hour. Okay, that's how we're going to actually create our equations here. 2, we're going to use Gauss-Jordan elimination to... maybe this one's just Gaussian elimination. I have to remind myself which one's Gaussian elimination and which one's Gauss-Jordan elimination. But either way, we're going to simplify the matrix in order to solve the system once we set it up. And then we have the question we want to ask and answer. if construction on 27th Avenue, so which one's 27th? Right here. If construction on 27th Avenue limits Z to 50 cars per hour, how many cars per hour must pass between the other intersections to keep flow going? So you would see this, sometimes when there's construction and you've got the person there with the sign, the like stop and slow sign, and they're letting people go through. Well, that slows things way down. So when you might normally get 500 cars an hour through there, you might now be talking about like 50, right? So then the question is, where do all those other cars go? Can they just take the long way? If you're going towards Victoria and you're like, forget it, I'm just going to go down to Johnson and catch the freeway down there, is that better? Or I'm going to go the back way, I'm going to go to Saticoy, or I'm going to go over to the collection or something. Like, is that better to go that way, or is it still okay to kind of go this way? Okay, so let's take a look here. So we're going to set up our system. Try to show this as much as I can. And we're good on time. Good. So here's what we do. We've got intersection I1. We're going to set up an equation for each intersection, right? So let's see. Let me catch my place. We have 1,000 cars an hour entering intersection I1, right? 700 from the west, 300 from the north. So 1,000 cars an hour enter intersection I1, which means 1,000 cars an hour have to leave intersection I1. Well, if you're leaving intersection I1, you're either going east on Palm Drive, or you're going south on 27th Avenue. So that's W and Z. So that's where they get, do you see over here, W plus Z equals 1,000? That's where they got that, was from equation number 1. So 1,000 cars an hour enter this intersection. They have to leave the intersection. Well, the only places for them to go are to be part of W and Z. So W plus Z equals 1,000. Okay, now we go to intersection 2. Well, 1,100 cars an hour are leaving intersection 2, which means 1,100 cars an hour are entering intersection 2. So it must be that W plus X equals 1,100. Do you see how each intersection is giving us an oh, it's not letting me highlight this anymore. There we go. Each intersection is giving us one equation. And then you play the same game for I3. 700 cars an hour enter I3, so 700 must leave. Well, that's X and Y. So X plus Y is 700. Over here, 600 cars an hour leave intersection 4, so 600 cars an hour must enter I4, and we get our fourth equation. Okay? So you have your 4 equations. You're going to turn it into, here's your system of equations. Notice up here it's a very compact way to write it, but it's kind of confusing because you've got W's and X's and Y's and Z's. If we write it this way, we kind of get that spatial structure again by adding in the zeros. And then we've got our augmented matrix that goes along with it. So that augmented matrix, you get a lot of zeros in here when you do that. So here's what your matrix looks like. And then you would put this in a calculator. I mean, you could solve it by hand, but you probably put it in a calculator. If you're an actual engineer, you'd put it into MATLAB or Maple or something like, whatever system you have, some computer algebra system. It's going to solve this for you, and it's going to spit out your answer right here. So this is the answer that it comes back with. Notice that we got zeros along the bottom. That gives us a dependency, which in this case is actually good news because that gives us a little bit of freedom with our solutions, right? So you simplify it down to this. And what you're going to do is you're going to reinterpret this back into a set of equations. So this first one reads as W, so 1W plus 0x plus 0y plus 1z equals 1,000. Or the way we normally write that, W plus z equals 1,000. Okay? Then we've got, remember, that's our W column, our X column, our Y column, our Z column. So this one comes out to be W minus Z equals 100. Okay, that's our second equation. And this one, W plus Z equals 600. And then we have zeros all the way across the bottom, which again, from the previous problem, remember, that allows us to pick Z. And when we pick Z, it's going to determine the rest of these variables for us because we're going to solve it that way. So I take W plus Z equals 1,000, and look what I do. I solve it for W, so that W plus Z equals 1,000 is the same thing as W equals 1,000 minus Z. But again, we're putting all these equations in terms of Z being the independent variable. okay? So the same thing here. I take x minus z equals 100, and I solve it for x to get x equals 100 plus z, and this one to get y equals 600 minus z. So now we have all the other variables, our dependent variables, in terms of our independent variable z. So we write the solution this way. This should look familiar. We have 4 things now, whereas the example we looked at a moment ago had 3. But I pick z. Whatever I pick for z, it determines what these other w, x, y are going to be. So remember in the problem that we were given, they said, what happens if we limit construction for z? Remember, z is the traffic over on this road right here. So if we limit that traffic to 50 cars an hour because we've got someone with the stop slow sign, they're standing there like, can't get through, you got to wait. Okay, now go slow, that whole thing. If we limit that to 50 cars an hour, well, see, notice how we put in 50 for z right here. And then all these z's in the rest of the solution, we plug in 50 there too because we've decided that z is equal to 50. So you plug in 50 for all of the z values, and when you do that, you get your solution. No, it's not letting me highlight correctly. So when z is 50, our w is 950, our x is 150, and our y is 550. So now you know, okay, if we limit the traffic on this street to 50 cars an hour, we now know the capacity that we need on the other roads. I need the capacity for 950 people an hour to get through W. We need the capacity for 150 cars an hour to get through X and 550 to get through Y. Now, you as a civil engineer will know at that time, no, that road can't handle 950 cars an hour. That's not going to happen. That's like a residential street. No way. Or, oh yeah, it's a main street. That'll be fine. People will complain and it'll be a little slow, but traffic will still flow. People will still get home on time. So using this dependent system, we were able to solve what is a fairly complicated problem, which I find kind of interesting. Is there any questions on that? Because we're going to move to a different section if there's no questions. Is everyone comfortable with that? Yeah, we're good. Okay, great. So that's in the book. It's on page 641. It looks like it seems really weird at first, but if you work through that example and you really understand each part of that example, it's not only going to help you understand this example, it's really going to help you understand the power of these dependent solutions and what you can do with them. So definitely helpful. Okay, then we skip a few sections. It's not that I'm choosing to skip them. They're not required for the course. Some of you will learn this stuff when you take a proper linear algebra class. You'll learn all about matrix multiplication and all this kind of stuff, which is kind of awesome. For those of you who ever used Photoshop or doing any kind of like I'm kind of, one of my things I'm learning about right now on my own is machine learning and programming artificial intelligence and stuff like that. Use tons of matrices. Every time you do something in Photoshop, like you're pressing a button and you're clicking something, it's really like matrices that are going on behind the scenes. So this kind of stuff is hugely, hugely important. So keep that in mind. Gaming, those of you who are big gamers, generally what's going on inside when your game is playing, it's actually usually got lots of matrix multiplications going on, and that's how it does shapes. That's how the background looks the way it does, and it can, as you approach something or you're walking down a street in a video game and then everything's getting bigger like it would in real life. That's all being done with matrices. Not like if you go back to old school, Super Mario Brothers, there's no depth of field, right? It was a lot easier because they just had a static background and then sure things were happening. But the background didn't really change as you got closer or further away. Now you play these open world games where you're moving around. As you get closer to something, it gets bigger. As you get far away, things get smaller. It's all matrices. It's all matrices taking place in there. So good thing to know. Matrix inverses, important topic, but not really something we're going to get too deep into in this class. Hugely, hugely important, but again, like many of you will get this down the road. And they have a little piece on here mentioning Alan Turing, sort of incredible individual, so smart. It's kind of the reason we have modern computers is largely because of the work that he did. Okay, then we're going to jump to 6.5, which is on page 675. And I think we have a good amount of time to talk about it. Good. Okay. So so they're talking about these things. This is Charles Babbage's difference engine. It's if you're ever just bored, just throw that into YouTube. I'm sure there's some interesting videos on this. In fact, I just watched a video the other day that was talking about analog computers as opposed to we're used to digital computers. But there are, partly because of machine learning is blowing up right now, there's a lot more work being done to sort of create analog computers versus digital computers and use them in different settings appropriately. So it's kind of interesting if you want to read about that. But, you know, you can look. There are cases throughout history where people have made these kind of analog machines where you, like, crank a thing and it calculates something. It calculates the way the planets are moving. Or it, like in this case, solves a system of equations. Or what was the other one, the Antikythera machine? What did that one do? I don't remember. But there's these machines that, like, sort of people can't figure out, like, how did they design that, like, 1,000 years ago? It's kind of amazing, some of this stuff. Anyways, we are getting into matrices. This is another way to solve system of equations, and determinants are a big part of that. Determinants are hugely important. There's two things whenever you deal with matrices that you almost always address. One is eigenvectors, which we don't talk about in this class, but it's one of those things where those of you who take linear algebra, you're going to see that eigenvectors are almost always important. At the very least, they represent, excuse me, I'm getting the hiccups. They represent meaningful things, but we're not going to get into eigenvectors in this class. The other thing is the determinant. The determinant of a matrix, hugely important. I mean, I remember when I first learned about matrices and we'd start applying them to these problems, and every single time it's like, here's why the eigenvector is important in this problem. Here's why the determinant's important in this problem. And they give you useful information. And I guess the reason that it's so surprising to me is when you first learn about eigenvectors, you go, okay, that's interesting, but like, big deal. And then you learn about determinants and you're like, that just seems like a bunch of chaos. How could that be anything meaningful? And then almost every single time you apply a matrix to something, the eigenvector and the determinants, they are important. So it's just kind of always surprising to me, like I say, because it seems like nonsense at first. But it absolutely is not. So what we do, the determinant, there's a few different ways you can define it. And the first time you see it, it's confusing. The determinant gets confusing quickly. Like I say, it just seems like a bunch of chaos. But it's sort of organized chaos, right? And once you get into it and you dive into it, you start realizing, like, oh, this isn't chaos at all. It's just that the complexity that's taking place is so deep that it's hard to see it immediately. With matrices, complexity can grow very, very quickly, right? Things you can do with a 2x2 matrix all of a sudden become very difficult with a 50x50 matrix. Like, the complexity just grows because there's so many combinations of everything. So we have this thing called the determinant. So I'll read this here. The determinant of a 2x2 matrix. The determinant of the matrix A1, A2, B1, B2. So notice the A's are in column 1, the B's are in column 2. And we denote it with the straight lines. So when you write a matrix, if it's a matrix, you always want to write it with these corners. So that way it's clear that it's a matrix that you're dealing with. If you use the straight lines, that's indicating a metric. And a determinant is considered a type of metric. A metric is where we measure something, like distance. Those of you who keep going in mathematics, you're going to learn there's lots of different ways of measuring measuring things, right? You can measure them in lots of different ways using different formulas. And depending on the formula that you use, sometimes things are better measures than others, or some have some advantages or disadvantages. And it's pretty standard. When we put straight lines around something, that means a measurement. The place you've probably seen this the most is absolute value. What is absolute value? It's two straight lines on either side of a thing, either an algebraic expression or a number. And what are you measuring with the absolute value? You're measuring the distance from zero. That's literally what the definition is. People remember it as like, oh, well, the absolute value just means you make it positive. That's not what it means. It's the distance from zero, right? So when you see straight lines in mathematics, you should always think, oh, is that a measurement? Because the answer is yes. Here we're measuring the determinant, which can literally have geographical interpretations, like lots of different things. So you're making a measurement. So how do we define it? Well, it's A1B2 minus A2B1, which at first you go, what? It's basically can be seen by this picture over here. Right? So who came up with A1B2 minus A2B1? It turns out it's the diagonal when you multiply this way, A1B2, and then you subtract the diagonal when you multiply this one, A2B1. So when you see it this way, it's easy to remember because you go, oh, it's the left diagonal minus the right diagonal, or whatever you want to call those diagonals. It's the first diagonal minus the second diagonal. That's a lot easier to remember. So this picture, oops, I'm pointing at the wrong screen. This picture is a lot easier to remember than this formula is to remember. Because at least here there's kind of some structure. You can kind of remember what's going on. And we say that the value of the second order determinant of this is A1B2 minus A2B1. But again, just think of it as those diagonals. That's specifically for a 2 by 2 matrix. Each time you deal with a bigger matrix, the determinant gets more confusing, right? And we are dealing with square matrices for these. So it'll be 2 by 2, 3 by 3, 4 by 4, and so on. Okay, so like here, how would we figure out the determinant of this matrix right here? Well, we'd take this diagonal, which is 15, so 5 times 3 is 15, and we would subtract 42, the product from this diagonal, and 15 minus 42 is negative 27. Okay, what about the determinant here? Well, that would be negative 10 on the first diagonal. Now, you have to really watch your negatives because there's a negative in your determinant, but also sometimes the values that you're using in the determinant are themselves negative. So look what we're doing here. We're taking a negative minus a negative. So keep track of all those negatives. It's easy to miss one. So this is negative 10 minus negative 12. Well, minus negative 12 is plus 12. So negative 10 plus 12 is positive 2. So the determinant of matrix B is positive 2. Watch all those negatives, okay? Keep track of them. Okay, so now we want to see about solving systems of linear equations in two variables using determinants. Now, why would you want to do this? Why would you want to solve systems of equations using determinants? Well, like, didn't we already have a way of solving systems of equations using Gauss-Jordan elimination on a matrix? And the answer is yes. Okay. I personally have never like implemented this in code or anything where I said, ooh, I'm going to use the determinant method for solving systems of equations. I haven't had to do that in my own research, but it's kind of handy because a lot of times in mathematics, especially as you get into more and more complicated types of problems, you'll have a way that you like to solve a type of problem, but sometimes that way has a weakness. And so you go, oh, this isn't the best way to do it in this circumstance. In this circumstance, I want to do it this other way. So it just depends on what you're trying to solve. So for right now, don't worry about too much about when you would use this. Just be aware it's an option. It's another way that we can use to solve systems of equations. I prefer Gauss-Jordan elimination, but determinants are really important, understanding determinants, and this is kind of an example of an early thing that you would use determinants for. Those of you who go on and you're going to, work on programs like Photoshop, you're going to see all these determinants behind the scene that tell you a lot about what you're, when you flip you've got something in Photoshop and you want to flip it upside down or you want to move it around, determinants are going to play a role in this kind of stuff. Determinants can play a role like in gaming when you have a shape and you want to shrink that thing down, but you want it to keep that same shape. The determinant ends up being part of that calculation. So they do play a meaningful role. Okay. So basically what you're going to do is we're going to calculate these different determinants, and then we're going to put them together in a formula and use them to solve our problem. So say we have a system like this. So we have a1x, a1x plus b1y equals c1. That's equation 1. a2x plus b2y equals c2. So see what they're doing? Our x's are all a subscript. So the subscript tells you which equation that's in, and the a tells you which coefficient it is. So a1, that's my x coefficient in equation 1. b2, that's my y coefficient in equation 2, right? So it helps you identify where things are located is all that it is. So they kind of they derive this here, and we're using a thing called Cramer's rule. So you'll probably hear about Cramer's rule when you're in calculus. But here's the idea: we've got our system of equations, and let me move it over a little bit. So we've got our two systems here, and this generalizes to higher degree systems of equations, but I'm going to have to show you. All we know right now is how to find the determinant of a 2x2 matrix. If I give you a 3x3 matrix and say find its determinant, you're going to go, I don't know how to do that. But here's what we do for Cramer's rule. So you've got what they call the coefficient matrix. So a coefficient matrix is just what you would think it is. It's just the coefficients, right? So see how you've got A1, A2, B1, B2? That's the determinant of what we call the coefficient matrix. And notice how it ends up in both of these denominators. So you're going to take the determinant of that. So you're going to do, diagonal minus diagonal, that whole thing. Now, what did they do in the top here in the numerator? Well, what they did, this is for the variable x. They took the coefficients in x and they replaced them with C1 and C2. Now, why did they do that? That's a very reasonable question to go, why? Unfortunately, I don't have time to talk about it, but it is on the previous page. So if you want to answer that question for yourself, they derive it right here. They derive where that thing came from. In fact, you can even see where the determinant came from. Does this look familiar? A1, B2 minus A2, B1. Oh, yeah, that's the determinant. Right, it's the determinant of the coefficient matrix. And then look what they got on top. Oh, well, that's what you would get if you took the determinant of the matrix where you took the coefficient matrix and replaced the A's with C's, you'd get this numerator. So it's one of those things where it's like we do it because it works. Someone figured out that this was a formula that works, and so we do it. All right, so you can see the derivation of where this came from. So because of time, I have to do a little hand waving, but many of you will do this more in depth down the road. And then over here for y, you replace the y coefficients with your C1, C2. And then you just calculate both of these determinants, and they will give you the answer for x and y. They give you the solution. So this would be a really easy thing to program. If you were writing a program and you wanted it to calculate determinants for a 2x2 matrix, pretty easy. Like we have the formula for the determinant of the denominators, and we can program how to, create this matrix, go through, take the determinant by multiplying these values, subtract these values, do the whole thing. Now, clearly we can see this doesn't work if the coefficient matrix has a determinant of 0. Then what's going to happen when you plug that into x or y? You're going to get 0 in the denominator. So that's an issue, but just kind of be aware of that, okay? So let's look at an example. I think we have time. Yeah, we have some time. I can talk about an example. So you have 3 different determinants that they talk about in this problem. They talk about d sub x. That's the one where you replace the x coefficients with your constants, with your answers. That's what dx is. D is just your coefficient matrix. And then dy is where you replace the y coefficients with the constants. Okay, so this is just a generalized version of what we're looking at up here, which would apply to any dimensional matrix, except the problem is we don't know how to find higher dimensional matrix determinants yet, but we will in a few minutes, okay? So they tell you D is just your coefficient matrix. Here's what dx is, and they go through and do the whole thing. So I think there's an example here, right? Yep, so here's an example. You're given and again, this would be easy to program in Python. I mean, it wouldn't even, I don't know, a dozen lines maybe, something like that, maybe more. But it wouldn't take very many. So you've got 5x minus 4y equals 2, 6x minus 5y equals 1. There's our system of equations. And we know that x equals dx over d and y equals dy over d. So we have to calculate those determinants. But it's pretty easy once you get the idea of like a diagonal minus the other diagonal. We're pretty much good to go, right? So you take your d, which is just your coefficient matrix. So 5, 6, negative 4, negative 5. That's what we get here. So we go diagonal. 5 times negative 5 is negative 25 minus negative 24. So it's really plus 24. So negative 25 plus 24, we get a determinant of negative 1. So that negative 1 is going to go in these denominators right here, right? Because that's what D was. Now we have to figure out the numerators. So now you do that. Okay, well now I'm going to take my coefficient matrix, but I'm going to replace, since this is D sub x, I'm going to replace my x coefficients with the constants from my problem. So the 2 and the 1 are going to replace the 5 and the 6 because those are my x coefficients. So now it's a 2, 1 here. Just calculate the determinant. So negative 10 minus negative 4 is negative 10 plus 4 or negative 6. Do the same thing for dy. You get negative 7. And then we know, okay, well, x looks like it equals 6 and y looks like it equals 7. And then you could go back and plug them back in and go, let's see, what was it, 6 and 7? Is 30 minus 28 2? Yeah. Is 36 minus 35 1? Yeah. So, in fact, that is the solution. So that was a pretty easy way to solve that system. Now, 2 by 2s are pretty easy anyways. But, you know, those of you who've done any kind of computer programming, you could go, oh, yeah, that actually would be not very hard to program in there. Okay? And again, if there's any questions, let me know. Okay, the determinant of a 3 by 3 matrix. So that looks like a fun formula, right? Have you got that memorized yet? No, it's a pain. But that's the definition of our third order determinant. You can see how each time we even increase the matrix in size by 1, the determinant gets way more complicated. What we actually have here, there's some very fancy math going on about how to remember these, because what we really have is these different versions of these different combinations of A, B, and C, where some are positive and some are negative. And there's different tricks. I hate to call them tricks, they're just mathematics, but there's like little tips that a person can use to help them remember which ones should be positive and which ones should be negative. And it just kind of depends on what you're studying. Like I studied a lot of combinatorics, and so you know, we would have these kind of things where you would create, we call them words out of letters. They're not like English words, but they're like combinations of letters like this. And then using the subscripts, you can remember which one's going to be positive, which one's going to be negative. I think that's probably a little complicated for what we're doing in here. So I'll show you a way that you can remember the determinant of a third order. In fact, there's a few different ways we can calculate these. So anyways, don't memorize this. It is not worth your time to memorize this. Kind of know what it looks like and go, oh yeah, isn't it a bunch of terms that all have A, B's, and C's in them? Yes, it is. And I mean, maybe memorize it if you like. If you like to nerd out on that kind of stuff, go for it. Whatever makes you happy. But I probably wouldn't memorize this formula. So here's a better way. There's a couple of different ways to calculate these. Let me show you one real quick. What page is that on? I guess in the update, they got rid of the picture that I liked. So I guess it's not in this new edition anymore. But I'll kind of show you, because here's one way that people can remember this. Page 681. Okay, so there's this pattern that you can go do to get the determinant, where basically what you do is you take your matrix here and you repeat 2 more lines. So see how they've added a 4, negative 9, 3? That's really the first column, but they've added another version of it over here. And then they took the 1, 3, 8 and they added another version right here. And you just create these like vectors. So you see these diagonals right here? You multiply down those diagonals and see these ones that are going to the right, you add those numbers. The ones that are going to the left, you subtract those numbers. So sometimes, a lot of times people, rather than just remembering a bunch of indices in that formula we looked at a minute ago, if people can see a geometric way, like a pattern that their brain can remember, sometimes that's better for them. So there's different versions of how to draw this. If you watch a video, you can watch different videos on YouTube. People will have slightly different ways of representing this, but that's one way that people can remember how to do the determinant of a 3 by 3. Not my favorite, but it's better than that formula that we were just looking at, right? That formula is awful. Wherever it was. Like, this is just kind of silly, right? And then imagine what a 4th order determinant is going to look like. You're going to memorize that one too? What about a 5th order determinant? You're going to memorize that one? So what's better is if we have a way, and we do, so to take away the suspense, we have a better way of calculating higher order determinants than learning a bunch of like crazy formulas that we don't who wants to learn a bunch of formulas? That's not really fun. Okay. So here's how we can figure out, they do this for a 3 by 3 matrix, but you can do this for an n by n matrix. So this is actually one way that you could use to calculate the determinant of a bigger matrix. Now what I'll say is there's a lot of computations. So you'd be surprised, it doesn't take a very big matrix where you sit down in MATLAB and say, calculate the determinant of this matrix, and it's not just coming back with an answer right away. You're like sitting there like, oh, what's going on? And you realize, oh, MATLAB is thinking. It's calculating my thing. It's just there's so many calculations taking place that you can very quickly get into something that's going to take a few minutes for MATLAB to figure out, even with a fancy computer. And it's because this method that we use is it's recursive. So recursive is something, and those of you who've had computer science, you've learned a little bit of this already. It's where you have something that's based on some previous step. And then like basically this thing just keeps feeding inside of itself and it does all these calculations. But what can happen in certain cases is if you have a recursion formula like the Fibonacci sequence, it's not necessarily going to get nasty. But if you have one where your size of your matrix is growing, that means each time you do the bigger determinant calculation, you have many, many calculations to do. So anyways, the point is it can get complicated quickly. But here's the idea, and they kind of do it a little bit strict. I want you to make sure you understand the generalization here and how this works. We do what's called expanding across a row or column, and you can expand across any row or column. And by being strategic, you sometimes can save yourself a lot of calculation by expanding across a particular row of columns, especially if it has a bunch of zeros in it. You're going to simplify a lot of your work and save yourself a lot of calculations. Also, if you're programming this, it can still be helpful. So here's what you do is you pick a row or column. In this case, they picked the first column. And what you do is you take this value here, so A1, and we put an A1 right here. And then what you do is you cross out, like not permanently because you're going to need it in a minute, but just for like a second, you can do this in your mind or if you need to do it lightly with a pencil, cross out the row and column that have A1 in it. And do you see what you're left with? If you cross out the row and column with A1 in it, you have B2, C2, B3, C3, and that's exactly what you take the determinant of. So we're taking A1 times the determinant of B2, C2, B3, C3. That seems complicated, but if you remember in this way where they're crossing out rows and columns, it's a lot easier to remember. So here the A1 you put the A1 there, you cross out that row and column, you take the determinant of what's left. Now you're going to alternate signs while you do this. So the next term you're going to subtract, but you're going to go to A2. You put that up here, and now you cross out the row and column with A2. And what's left? B1, C1, B3, C3. You take the determinant of that. Now you alternate the sign again, so it's back to being positive. You put your A3, you cross out the row and column with A3, and you take the determinant of B1, C1, B2, C2. See how there's a pattern to it? So what we've done is we took a 3 by 3 matrix. We want to calculate that determinant, but what we've done is we've broken it down into a bunch of 2 by 2 determinants, right? And so you can see how this thing would get computationally difficult very quickly, because we took one 3 by 3 matrix and turned it into 3 2 by 2 matrices. Well, that doesn't seem too bad, right? I mean, your computer would calculate this, before you even notice time passing. But what if you had a 10 by 10 determinant that you wanted to calculate? Well, you would turn that into 10 9 by 9 determinants. And then how would you calculate those? Each of those 10 9 by 9 determinants you would turn into 9 8 by 8 determinants. And then each of those you would turn into 7. Let's see, do I have my indexing right? You turn it into a bunch of 7 by 7 determinants. And then each of those would turn into a bunch of 6 by 6 determinants, all the way down till you got to a whole string of, like, in that case, what I just talked about would be hundreds, at least hundreds, maybe even thousands of 2 by 2 determinants. And then your computer would go through and calculate all those 2 by 2 determinants really quick and add everything up. So, if you wanted to figure out the determinant of a matrix that was 50 by 50, you might be waiting a while, right, depending on the situation. That's why sometimes you go, oh, well, let's not use this method. Let's use another method. Or maybe for this particular problem, there's a more clever way that I can do it. Okay, so that's how those determinants work. So you're probably going to have to look at some problems in the book to make sense of it, but follow along. It just comes down to pick a value, cross out a row and column, and remember that your signs are alternating plus minus along the way. So remember to do that. And they kind of give you a little bit of help. See here, they're expanding across the middle column. That's totally allowable. You can expand across any row or column that you want to. And you can see they kind of give you the pattern here where it's like you've got your pluses and minuses, so you can remember like which plus or minus you should be applying up here. Because if you start in the second, let me show you. If you expand down that second column, where did it go? Where did they do that? Wait, didn't we just have a problem where they did the second? Oh, down here. Notice that you start with a negative and then it goes plus minus. So the problems we looked at went plus minus plus, but this one goes minus plus minus. That's because you're expanding down the second column. So that's what that's what this is showing you, is like it's showing you the signs when you expand across a certain row or column. Okay. Now, here's why this is useful, or here's one way that you want to look out for. See how this column has 2 zeros in it? Well, look what that does. That means whatever this determinant is, you're going to multiply it by 0, meaning don't even calculate this determinant because it's about to get multiplied by 0. Same with the second one. Who cares what this determinant is? We're about to multiply it by 0. So this whole big calculation for this third order determinant actually just comes down to this little piece at the end. So when you're expanding across a row or column, just take a look to see if you have a row or column that's going to be easier to expand across, especially if you have a bunch of zeros in that row or column. Probably want to expand across that one. You never really know, but that's kind of the way. Okay. Oh yeah, so then we've got the 3 by 3 using Kramer's rule. It's the same thing as 2 by 2. It's just now you have bigger determinants to calculate. So it's a little bit harder. But you see the same formulas. We have an extra variable of z, but you're going to play the same game with z. Determinant of the coefficient matrix goes in the denominator, and then In the numerator, you're going to take the determinant, but you're going to replace the z coefficients with your constants. Okay, is how that's going to come out. So nothing too wild or crazy right there. Oh, and then they say, well, what do I do if the determinant of the denominator in Cramer's rule is 0? If d equals 0, the system is inconsistent or contains dependent equations. So basically, you should use another method than Cramer's rule, like Gauss-Jordan elimination or something like that. So this is a nice, quick way to calculate. If you had to program it yourself, I would much rather program Cramer's rule than program Gauss-Jordan elimination. It can be kind of a pain sometimes because of certain considerations you have to make. But Cramer's rule is a little bit, it can run into issues with all the determinants that you're calculating. So for a big enough system, I think Gauss-Jordan elimination is going to be vastly faster than the determination method. If you had to calculate some like really massive systems of equations and you had to simplify it, I would think that in general, it's been a long time since I looked at this, but I believe Gauss-Jordan elimination for big problems is going to be faster than Cramer's rule. But if you're just dealing with small problems, Cramer's rule is probably going to be easier to program than Gauss-Jordan elimination. So it just, that's kind of what it means to be a thinker and a engineer or scientist or mathematician, is you kind of look at every problem differently and go, okay, what makes this problem interesting? What's the best way to approach this problem? You can't just memorize a bunch of stuff. You got to be able to think your way through problems. Oh, also you can't use Cramer's rule on a non-square system. Doesn't work because your determinant, you can only find the determinant of a square system, right? Okay, that should be what we need. Let me just double check everything's like it's supposed to be. Go in here, modules. Oh, kicked me out. Let's go back to here. I think everything should be good. Yep, chapter 6 is up. I'm getting chapter 7 prepared right now. So you should be good with all of this. There's some videos in here that kind of walk you through it, plus everything that I just talked about. I think you'll be good for in here. If you're still confused on Cramer's rule, there's other YouTube videos that you can watch and get a sense of that. By tomorrow, I should have the chapter 7 stuff up, and then we'll talk about the remaining conics on Thursday. Tuesday of next week, we're going to talk about sequences, series. Those end up playing a big role in what I think. I forget if they have it now. When I took it, it was the last thing you learned in Calc 2, where you go like more in depth with it. Sometimes they might teach it at the beginning of Calc 3 now. I think it depends. I don't remember. I haven't taught Calc 3 in a while. But we'll do that on Tuesday. So I'm getting all that stuff ready for you. And then the Thursday after that, so the Thursday of next week, is your test. So just before we go here, remember, you've got an extension on some homework assignments. So those of you who want to still get those points, go for it. If you are planning to do the retake, just remember your retake score will replace your original score, even if it's worse. So kind of make that calculation for yourself. Honestly, if you got a decent score on the first test, you're probably better off studying for the second test anyways, rather than restudying for the first one. But it's up to you. You know, some of you want to get straight A's. Some of you just need to pass the class, kind of whatever, right? So, whatever in the sense that, like, you can decide what makes the most sense for you. You're the only one who really knows your path in life, right? Even if you don't know it yet, I certainly don't know it better than you, what you should do. So, you make that decision about what you want out of a grade, if you want to retake that test or not. If you're going to retake it, jump on that today and try to get that appointment set up today so that you can be all ready to go for next week. You don't have to, trying to make the appointment next week could be tricky. So take care of that. So let's see. So what I say, homework, the retake, and then you have a test a week from Thursday. So all that stuff. And then we're out of time. So I will turn off the YouTube stream, and then I will sit around in Zoom and help anybody who wants to ask me questions or talk to me about stuff or need some clarification on homework or anything like that. Come talk to me. Okay? Otherwise, I'll see everybody in a couple days. Thanks, everybody.